In this video, we're going to discuss a common discrete probability model, the Poisson. Let's start with an example. At a certain rural intersection, cars pass through at an average rate of 3 per hour. Further, 80% of these cars have Minnesota license plates. Consider the first question. Suppose we watch 5 cars go by, and let X be the number of these cars that have Minnesota license plates. In this case, we know that X can be 0, 1, on up to 5 cars. Further, we have n equals 5 fixed trials. Each trial has a binary outcome. Either a car has a Minnesota plate or it doesn't. And these trials are independent, each having a 0.8 probability of success, p. Thus, X is binomial with n equals 5 and p equals 0.8. Consider another example. Suppose instead that we wait at the intersection for 1 hour and let y be the number of cars that pass by during that hour. We might see 0 cars, 1 car, 2 cars, 3 cars, which is typical, or 4, and on and on and on. That is, the number of trials in this experiment, or the number of cars we might see, is not fixed. We're just observing the number of events in a given period of time where there's technically no upper bound on the number of events that might occur. Thus, y in this case is not binomial. Rather, y is Poisson. Now, before stating the probability mass function related to the Poisson, consider the following scenario. We know that y depends on the rate at which events occur. The plot here shows the values of y, or the number of cars we might see during our 1 hour observation period, assuming a rate of 3 cars per hour. Most commonly, we would see maybe 2 or 3 cars. And since cars only pass by at a rate of 3 per hour, it's unlikely that we'd see more than, say, 10 cars. However, if we consider a busier intersection where cars pass at a rate of 10 per hour, notice that we'd most commonly see 10 cars per hour. Further, it's not very likely that we'd see as few as, say, 2 cars, or as many as 18. In fact, both scenarios provide examples of a Poisson model. On the left is the PMF of a Poisson model with rate 3, and on the right, a PMF for a Poisson model with rate 10. In general, let random variable x be the number of times that an event occurs in a given interval of time or space. Further, suppose that the rate at which these events occur is lambda. Another way to think about lambda is as the expected or average number of events that occur in that interval of time or space. In this scenario, then, the random variable x has a Poisson model with rate lambda. So lambda here is the only parameter upon which the Poisson model depends. Thus, as we saw in the previous slide, lambda controls the behavior of a Poisson model. Next, consider the Poisson probability mass function, f of x. Since x is discrete, fx can be interpreted as the probability that x equals little x for values of x from 0, 1, 2, and up. This probability is then calculated by e to the negative lambda times lambda to the x over x factorial. Let's consider a couple more examples. At a local fossil store, customers arrive at a rate of 1 per hour. Let x be the number of customers that arrive in the next hour. In this case, since we're looking at the number of events that occur in an interval of time and that occur at a fixed rate, the Poisson provides a reasonable model of how the customers might vary from hour to hour. Specifically, with a rate of 1 customer per hour, we can model x by the Poisson model with rate lambda equals 1. Plugging lambda equals 1 into our formula for the Poisson PMF, the PMF of x is defined by e to the negative 1 divided by x factorial. Again, technically, we could see 0 customers, 1 customer, on up to infinitely many customers. However, the plot of the PMF here suggests that we're very unlikely to see more than 5 customers in an hour, since they only arrive on average 1 per hour. Now, what about if we wanted to calculate the probability of a specific value of x? For example, what's the probability that we observe 2 customers in the next hour? The plot of the PMF here suggests that this figure is just shy of 0.2. For a more precise measure, we can evaluate the PMF at x equals 2. Then the probability of observing 2 customers in the next hour is roughly 0.184. Next, let's change our time interval. Suppose that the store is open for 8 hours a day and that customers arrive at a rate of 1 per hour. Further, suppose we're interested in y, the number of customers that visit the store tomorrow, not just during a 1-hour period. Since there's 1 customer per hour and the store is open for 8 hours per day, then we can assume that customers visit the store at a rate of 8 per day. In this case, our random variable y is still Poisson. We're still observing a count of events in a given interval of time, but here the events occur at a rate of lambda equals 8. A plot of the corresponding Poisson PMF shows that, since we're expecting 8 customers per day on average, the values of y around 8 per day are most common. It would be uncommon to observe, say, 0 customers in a day, or as many as 17.